Okay, so I think we can get started. Pretty quiet today, so that's fortunate that we're also launching a newish chapter, new unit in the course. Good, I think we are in a good setup. So we'll start with some announcements on where we are in the class. So I'll reserve some of this discussion about how to develop correct software and the approaches that we use in this class and our assignments to make correct software. I'll reserve this discussion to Thursday, where we'll have more of a live attendance. And we'll go to some announcements. So just kind of viewing what are the immediate things that are due coming up in this course. So due tomorrow night, Wednesday night, there will be there will be quiz 3, which is about more review of pointers and memory and allocating and freeing memory. That will be due tomorrow night. Programming assignment 2 is out and will be due Friday the 23rd. This is a full-size assignment worth 150 points. It's got 6 parts to it. And as always, it's important to keep pace. Now that we're a couple days into the week, it's probably a good idea to at least have opened the assignment, taken a look at what it's all about, and maybe even attempted and completed the first piece of that assignment, right? The first part is called edge list, and is meant for you to get used to what's the infrastructure for programming assignment 2. The next unit in the class is Chapter 2 of CSAPP, the textbook. This is a chapter that's all about how information is encoded in all modern computers using binary, both in terms of integers and also floating point numbers. So floating point numbers is important that you know how they are encoded, because this is a nearly completely, totally universal standard in all modern computers. And being able to work with bits and bytes, this is a fundamental skill in computing, because there's just all kinds of settings where unexpectedly you would be dropped down to having to look at a number and figure out what it is at the bits and bytes level. I'll give you some examples of this level of bits and bytes work in a little bit. So first is some motivation. So what we'll do as kind of structure for today's class is we'll talk about, even before reaching how numbers are encoded in whole, we'll talk about just bits, working with bytes. And then, if we have time, then we'll get to the unit which is about representing larger numbers, the actual integer encoding. So we would be interested in how to represent numbers of various ranges. And we're also interested in encoding negative numbers. And here is an interesting design study, a deep dive into various options. And why some options are better than the others. So this is, I think, an interesting and fun piece, because it gets you thinking about, what is a good design and what are various trade-offs. Okay, so It's nearly a kind of fundamental assumption now that all computers represent information as binary numbers. But the interesting thing is if you open up a computer and you take a look at the signals that are on the computer on the motherboard or in the CPU or on the main memory bus, you won't ever actually see a signal that's literally 0, 1, 0, 0, 1, dot, 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 right? This is completely an abstraction. What you would see is just squiggly lines on a wire encoded as voltage. So typically this would be something like 1.5 volts down to 0 ground voltage. And over the course of time, all you have is just this kind of analog signal, continuous time, continuously changing signals. And the advantage of abstracting things as digital binary is what you would do is instead we define everything above a certain range as 1, everything below a certain range as 0. Now, this is just the values, right? So we need to think about physical systems as having several properties. There's the value encoding, there's the spatial extent of things, and there is the time extent of things, right? So just simply saying that, okay, in terms of the values here, that's the 1 range, that's the 0 range, that's not enough, because still you have all of these segments between 1 and 0 where there would be no correct definition of what that value is supposed to be. So in addition to defining the signal range, all computers operate on a discrete time clock, a drum beat, that defines when values are well defined, right? So we may say something like, okay, the value at that time point is valid, the value at that time point is valid, the value at that time point is valid, the value at this time point is valid, and at this time point is valid, right? So each of these time points, the values are in a well-defined, unambiguous. So here's a 1, here's a 0, here's a 0, here is still 0, and then here it's going to be 1. Right, so this is how we are able to safely throw away all the ambiguous intermediate time points. And this clock signal, typically one way we would define what this clock signal is we can say something like, okay, we define the clock signal time point as times where the clock signal is a rising edge. Right, the clock signal itself is a continuous time signal where it's a square wave, and so we would say every time this signal is about to rise to above a certain threshold, that is the time point that we sample the signal. So this is the motivation for binary encoding. It's really useful because it disambiguates and is a reliable way to store information. And of course, right, this wasn't necessarily always true. There's a kind of side note here of kind of a story of the history of computing. Before computers were all digital, they were indeed analog computers. So these are computers where the signals are encoded as continuous time, continuous value signals. They use these things to, say, solve for trajectories. This was in the, say, 1950s. Then they realized, well, it's very useful to define this 0-1 abstraction and discrete time evolution. And so by the 1960s, basically all computers were encoded using this digital paradigm. But even more recently, say in the 2010s and beyond, especially in particular, even more recently, the more recent era, we're breaking this abstraction yet again, right? So we're able to manipulate physical systems to the extent where they're quantum mechanical statistics and behavior reigns. And people are learning how to build computers where the signals are not just 0 and 1, but can in fact be simultaneously 0 and 1 in these quantum mechanical superposition states, and use that to create even more incredibly sophisticated algorithms, right? So this is just kind of a side note here. Okay, any questions so far? So with this, some of this should be basically review of how numbers are encoded as binary. So the thing here is we need to know that number systems are something that is defined, right? It's a kind of standard, right? And in addition to kind of the decimal number system that we're so used to, right? Why are we used to decimal number systems? You know, any guess why is everything in real kind of day-to-day life decimal as opposed to something else? And you know, we can answer over the Zoom chat too. I think we're set up. Okay, so Maya says base 10 is easy to work with. Zunair says it's easy to read. All of those are fine, but you could say the same thing about a base 8 system or a base 12 system, right? Arguably, a base 12 system is even more convenient. Why base 12? Base 12 has a lot of factors, right? There's many, many ways to split 12 into equal parts. You can make it 12 of singles, 6 of pairs, 4 triplets, 3 quadruplets, right? Or 2 sets of 6. So arguably base 12 is more useful. That's why there are actually many things in day-to-day life that are base 12. Time is base 12, right? We got 12 hours per half day, 12 months in the year. And yeah, so everybody on the Zoom chat has got it, right? This quirk that we use, base 10, is because we have 10 fingers. It's just kind of a historical thing, right? And Alex says, we like powers of 10 still. That's maybe true. Powers of 10 may seem natural because that's what we've grown up all our lives with. But if you were used to a base 12 system, you would think, hey, powers of 12 are equally intuitive as well. So in computers, right, basically because all the signals are binary, time to time, we have to write down numbers as binary. So the way you interpret binary is just like in base 10. Let me just create a new page here. Just like in base 10, you have all these digits. You have the ones digit, you have the tens digit, you have the hundreds digit, you have the thousands digit, you have the 10,000s digits, and you have the hundreds thousands digits, and so forth, right? And when we write down numbers as base 10, say 900,000, 90, and 9,000, 999, this is performing a calculation, right? What this is really saying is 9 times 100K plus 9 times 10K plus 9 times 1,000 plus 9 times 100 plus 9 times 10 plus 9. This is, well, in shorthand, it's 1 million minus 1. When we want to decode a base 2 number, it's basically the same idea, right? So we have a base 2 number. I'll create a lot of digits here and see how far up we can go. So what's the first place? All right, in the first place, we've got the 1's digit. Then we have the 2's digits, 4's, 8's, 16's, 32's, 64's, 128, 256, 512, 1024. Who on the Zoom and also in the classroom, how many of us have beaten the game 2048? Say aye. Okay. All 4 of us in the room. Anybody has anyone played up to, okay, that's enough of the eyes. How many have played up to the next level? Who's done the next level beyond 2048? What would that name, what would that game be called? 4096. Okay, so we've got in the Zoom chat 4096. Who's beaten 4096 before? No one in the room. Anybody in Zoom? Okay, Kayla has beaten 4096. Who's beaten the next level game? What would the next level game be called? $81.92. Who's beaten $81.92? Okay, nobody, right? So yeah, anyway, the names of these games are just powers of 2, right? You could, each doubling of the goal square that you're trying to get ostensibly doubles the length of time it takes, the number of moves needed to beat that next level, and the board gets more and more crowded, right? 2048 is this nice little trade-off. It basically takes about half an hour, just swipe around to finish 2048. So how do you decode a base 2 number? Well, same idea, right? If we write down a bunch of 1's in every single digit, really that's telling us to do a computation. The computation is 1 times 1024 plus 1 times 512 plus 1 times 256 plus 1 times 128 plus 1 times 64 plus 1 times 32 plus 1 times 16 plus 1 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. What will that evaluate to? If we add all these numbers up. Oh, come on, I'm sure it's somebody on somebody's tip of tongue. If we add all these numbers up, yeah, so we've got it in the chat. So Zanir guesses is 2048. No quite. So Matthew says it's 2047, and that's the correct answer, right? This is going to be 2 to the 11th minus 1, which is 2048 minus 1, which is going to be 2047. Right? The way that we saw this so quickly is to observe that 2 to the 10 is 1024, right? And by summing up all of the subsequent powers, we get the next power of 2 up, 2048. So this is binary systems, and we'll get a lot of practice in all kinds of different settings throughout the next couple to 3 weeks. We can also do base 8. And a couple weeks ago, we had a little discussion, right? What's the significance of base 8, right? We can motivate why base 10 is important. We can motivate why something like base 12 is very useful. We can motivate why base 2 is fundamental, since we're using zeros and ones to encode numbers. What's so special about base 8? Well, arguably, there's not too much that's super special about base 8. ASCII, the encoding for letters and symbols, requires 7 bits to represent all the characters that you see on the keyboard, uppercase, lowercase, numbers, symbols, and then plus a bunch of other control symbols. That needed 7 bits, and 7 bits are kind of odd and prime number. So as a useful grouping, we write down bits as sets of 8, and we call this a byte, right? 8 bits to a byte. And so it could be useful to sometimes write down numbers as base 8. So for base 8, same approach. We've got a 1's digit, we've got a 8's digit, we've got a 64's digit, and then we have a, what's the next up? 5/12's digit, right? And for these numbers, say that you want to calculate some number, 011, represented as base 8, octal. Well, what this calculation is telling you to do is 0 times 512 plus 1 times 64 plus 1 times 8 plus 1 times 1. What does that evaluate to? 64 plus 9, so 73, right? So going back a slide here, yeah, so that's an exercise in writing down numbers as binary and octal. And when we denote numbers as decimal, we usually write things down just as we're used to, just in plain old decimal numbers. But if we're writing down in binary, one custom that we have is to emphasize that it's binary. So we say that it's 0B to indicate that the subsequent number, you as a human being should read that as a binary number. And this is what the C language expects, right? So in the C language, if you write down numbers as 0B, ... the C compiler will understand that number as a binary number. The convention for writing things as octal is to write it with a 0O. And same thing, we've already encountered some of this, which is for base 16 hexadecimal, the custom is to write it down as 0x, x meaning hexadecimal. A really, really major gotcha, right? A really, really major gotcha in C programming is if you write down a number, let's see. Right. So if you write down a number, I say I want to printf %d/n. So I'm writing down the number as a decimal, and I give it this. What will this print out?
Would it just print out 10? Would it not print out the 0 in the front?
So thanks for joining in. Yeah, no problem. Let me just dial down the volume a little bit. So one guess is 10. We got somebody say it's 10.0, which is not quite. It's not going to print out 10.0 because we're not specifying it as floating point. Let's see, right? Let me see how quickly I can change screens here. I think this is worth doing a quick demo for. Stop share. So here we're in my laptop now, and we're on iLab. And let's experiment this for really quick. So we're just going to print that statement, right? Printf, which will need import. So let's see. It's on IO. And I want to printf %d/n, the number being 0, 0, 1, 0. It prints out 8. Anybody want to interpret why? This is a very tricky gotcha in C. So Nicholas guesses right, it's an octal. So what is it that caused it to interpret it as an octal? Yeah, there's a 0 at the start, right? And I'll tell you, the first time I realized this in school, I was like a senior and I was doing some project and I realized, wait, you can't just pad zeros at the beginning in C. Yeah, so when you have a leading 0, the C language definition treats this as an octal, right? So sometimes you'll have very cute situations where I intend well, right? I want to print out numbers. I want to print 10, and I want to print 100, and I want to print 1,000, right? This is just hypothetical. I want to print these numbers, and you look at this code and you want to make things all line up, so you intend well, right? I'm just going to pad the integers with some leading zeros so that the code lines up well and it's easier for you to verify visually that the code is correct. This is a very tricky gotcha. Padding zeros at the beginning causes C to treat this as a octal. Anybody who's aware of this, anybody who want to tell us whether this is true for Java or not? Right, I'm sure somebody can look that up real quick. Is this standard inherited into Java?
Yeah, I'm opening up Eclipse right now. It just takes a bit to load.
You could try it in Eclipse, or you could try it just look up the Java language reference, the manual for Java, and see if it inherits the same. right? So I'll let you guys run that experiment to see if it's true also for Java. Anyway, so this is probably one of the more useful gotchas, right? Don't make this mistake. If you pad zeros in C, it's a very annoying standard that the leading zero causes it to interpret as octal. Okay, so this next slide here just emphasizes the same idea a little bit. I'm interested in representing the decimal number, 255. And to represent 255 as binary, well, 255 so happens is 256 minus 1. And we know that 256 is 2 to the power 8. So this number is going to be the binary number 0, 1, followed by 4 zeros, making that 2 to the power 8, right? That's a ones digit in the 2 to the power 8 digit, minus a 1, which makes it 0B, 1, 1, 1, 1, 1, 1, 1, 1. 4 ones, right? So this is a quick way to figure out how you would write 255 as a binary number. And for octal, well, octal, this is a little bit less intuitive, right? It's a little bit less natural. For octal, then we have to work through the individual bits by bits, or sorry, the digits by digits in octal. So remember, in octal, we have 0, O, indicating that it's an octal number, and each place is going to be a power of 8, right? So we've got the ones digits, we've got the eighths digits, we've got the 64s digits, and we have the 512 digits. So to figure out how to write 255 as octal, what you have to do is take 255, divide by 64, that gets you 3 and then something, right? So what is that going to be? 264 times 64 is 192. 255 minus 192 is 3 and a 63. So it's going to be a 3 in the 64th digit. And to figure out how many in the 8th digits there are, you're going to have to take 63, divide by 8. That gives you 7 times 8 is 56. And you have 7 remainder, and that goes in the ones digit, right? So to represent 255 as octal, it's going to be 0, indicating octal number 377 is the octal for 255. And finally, right, just as to kind of conclude this slide, to write down hexadecimal, there's a couple ways, right? If you want to convert a number from decimal to hexadecimal, you have got a couple ways. One approach is to go directly to hexadecimal, right? If you go directly to hexadecimal, what you would do is the same approach, right? Each digit in the hexadecimal number, you've got the ones digit, you've got the 16th digit, you've got the 256 digit. So you would write down, okay, you've got 255, so that's going to be 15 in the 16th digit with 15 left over, right? That's one approach. Another approach is you take the decimal, you write down the binary, and then you look at the binary and convert to hexadecimal, right? So here we already have the binary, it's 1111, 1111. So 8 ones. What you do is you group 4 bits at a time, right? So what's 1111, 4 bits, all 1. That's 15. So I've got a 15 followed by a 15, and how do we represent 15 as hex? This is F. Yeah, so binary is 0B1111, 1111. Right, so sometimes I'll write down a underscore to emphasize, to visually group the bits so it's easier to read, to see that this is 4 ones, 2 groups of 4 ones. And you look at that, that's 15 and 15, so you can write down 0x, F, F, indicating the same number. Okay, before we move to the next little exercise, anybody can get back to us on whether Java has that quirk or not?
It does the same thing.
Does the same thing. So in Java, if you do system.out.println 0, 1, 0, what does it say?
It prints out 8.
Yeah, and we've got the Zoom chat up, right? So who knew about that before? Who's so diligent about the details of Java that you memorize this? So we've got some, yeah. Oh, hold on, I gotta scroll. Okay, so Pascarino says, yeah, never knew this, right? Even in this class where we're studying C, you'll still learn very bizarre things about Java, right? And so don't fall into that same trap. Okay, cool. What's a place that we'll encounter, right? You tell me, right? You know, you only learn about hexadecimals in CS211 because that's a low-level computer architecture course, all right? And maybe we'll do this exercise, right? Where else in the real world would you encounter hexadecimals? Colors, okay, so that's what we'll do next. Hex codes for colors, very, very real, you know, non-computery thing where hexadecimals show up in day-to-day life. Where else? Memory addresses, okay, well, sure. But you would say that memory addresses, that's definitely something that we learn because this is CS211, right? Computer architecture, you gotta learn about memory addresses. So let's play this little game. Let's interpret some hex numbers. So anybody want to quickly explain how hex codes encode colors? Okay. Yeah, go for it. How do you encode colors?
There's like 6 set of letters, and each letter represents like no, there's like 2 letters, and each one represents the color. For like one for red, one for green, and one for blue.
Yeah. Okay. So we've got 6 digits. You've got 6 digits, 6 hex digits. Each pair encodes the density. Oh, I messed that up already. The density of that color for the color. So this first color here, hash code 000000, says this color is no red light, no green light, no blue light, right? Which, based on how light colors combine, this color is going to be black, right? There's no color light components for each, right? And then we learn in, say, physics, the way that the human color system, human eye interprets color is that if you mix red light, green light, and blue light at the intersection of where all those light colors are combined, that if the intensities are correct and the component colors are tuned correctly, at the intersection you'll see white color light, right? And keep in mind, this is about light colors combinations. If you're talking about pigmentation color combinations, that's a different color system. What other color system is that? Right, there's also the CMYK color system, which talks about how ink colors combine. Right, I'm talking about here in this slide, I'm talking about light colors. So this is why this hex code, 0xFF, well, what this color code encodes is FF of red, FF of green, FF of blue. And really what this is saying is I've got 255, 255, 255 of each color light, and we define them so that maximum intensity is 255, right? So the color is 0xFF, that's white color light. And then the next one is, say, this color here, right? This medium-ish gray. So how do we figure out what this color code is? What's 6A? Yeah, what's 6A as a hexadecimal? 0x6A as a decimal number is going to be?
106.
How did you figure 106? So it's 6 times 16 plus, what's A? A means 10, right? So 0 times 16 is 96 plus 10 is 106. So it's 106 density of red. And what's 7.5?
That's 117.
So that's 117. So 0x75 equals 7 times 16 plus 5, which is 117. And 7c?
I think you wrote 177 by accident.
Oh, sorry. Good catch. And 7c? 0x7c is 7 times 16 plus c. What's c? A, B, C.
12.
So 10, 11, 12. Yeah, so 12, this is going to be 124. Right, and so if you look at all these color densities, 106, 117, 124, they're all kind of right in the middle, right? They're right in the middle between 0 and 255. So a little bit of red, a little bit of green, a little bit of blue gives you this medium-ish gray. And you may be wondering, right, what's so significant about this code here? We'll leave you to guess what that is. And as just kind of a fun exercise, what's this next color roughly going to be? Hash code CC0033. It will be red dominant. Okay, but then Zunir said, oh no, it's going to be green. Right, so this is kind of fun. So 0, just finish this exercise, right? Let's figure out what CC is. What's CC? CC 0033. So CC what's C again? 12. 0xcc equals 12 times 16 plus 12. What's that going to be? 204? 204. Okay, we got multiple sources confirming 204. So it's 204, which is pretty densely red, right? Red dominant, that's right. 0, 0, trivially, we know that that's 0. And 33 is not 33. It's 0x33. And what's 0x33? So 3 times 16 plus 3 is 48 plus 1, plus 3 is 51. So it's red dominant with a little bit of blue. Right, so anybody want to guess what that color is? Maroon, okay. So reddish magenta, all right. So we got a lot of school betrayers here. We've got maroon knights, we've got reddish magenta as knight. Robert has it, it's Rutgers Scarlet, right? This is the standard definition. If you go to a document called the Rutgers Visual Identity document, somebody high up in the university has defined, they go through the archives of all the red colors that have represented Rutgers, and when the internet came around, they were like, we need to define what Rutgers Scarlet is, right? And they measured everything and figured out that this hex code CC0033 is a good representation of Rutgers Scarlet, right? And this other gray here is also the standard Rutgers, right? So both are Rutgers colors. Cool. Next little thing, we already did this piece of code. So this is in our PA0 directory. There's a little code called ASCII.c, which just goes through all the possible values of a single byte, prints it out as %C. And sees what happens, right? So this will print out a bunch of characters, and here is kind of the ASCII table. This is one representation of it, but there's also other more readable tables online. Okay. So one other setting, right? I think just to motivate that bitwise operations are important. You know what? Let's change screens now. Let's go ahead and switch to the laptop. Stop share. Good. And share screen here. So we've got that ASCII code program that I just talked about. It is in PA0 ASCII. Right, so all this code did in our initial demonstration was to print out the digits 0 to 255, all of them, and interpret that number as a %C, right? So I'll print out the digit, and then I'll print out that as a character. We can run this program. And this basically prints out the ASCII table on our behalf, right? And you can correspond the familiar characters to the ASCII table to convince yourself, yeah, indeed, the percent symbol is encoded as the number 37. Many of these will be normal characters, uppercase, lowercase alphabets. A lot of them will be undefined, right? Remember, ASCII only uses up 7 bits, so anything beyond 127 is undefined as a character. But back here, you have a bunch of these very strange gaps, right? So some of these will skip a line, some of them will somehow consume some characters, and these really are just different forms of new line and different forms of backspace. And there was even a kind of fun one, the digit number 7. If you print out just the digit number 7, it is the typewriter ding, or typewriter bell. And this standard that the digits 7 printed as an ASCII character should trigger the typewriter ding. That is carried through even today, right? So if you print 7 as a character, it will do the screen flash and ring the computer bell. The next thing that I wanted to do, according to the slides, is being familiar with hex codes or binary representations, such as the color code, shows up in other areas too, right? So even in this program here, so I've got my ASCII program. I've got it compiled to a.out, right? This is our program running. Previously, I also compiled this to a named executable called ASCII, so it doesn't just put the executable in the standard name a.out. So I've got my ASCII program called ASCII here. And the reason that we're able to do this, right, we're able to say /ASCII and it runs a program, is because if you say ls, which lists files, and you give it LA, which helps it show some more verbose information about this file, there are these flags, right? The file mode of this file. It also tells you other information, such as who owns this file, the size of the file, and the last modified timestamp, which is just now, of the file. The place I want to direct your attention here is this sequence of characters here. Right? This sequence of characters here is the Unix. Linux is a kind of Unix. It's the Unix file permissions for this ASCII file right now. And this is telling me, based on 3 different user groups, you, the first set, me, the user, I can read this file, I can write this file, and I can execute this file. The second group of 3 characters is called the group, right? So I can, in Linux, say group or groups. This tells me that I, as the logged in user YH804, that's my uni or my net ID, I belong to these groups on the iLab machine. And so anybody who is a member of one of these groups will also be able to read this file and execute this file. And finally, the last set, right? The very last set is everyone, right? This is anybody who's logged into the iLab machines. So we can modify this, right? We can modify this. I could do things like change. So chmod, change mode. This modifies the permissions on this file. And I can say u minus x, so me, the user, I'm going to subtract the executable rights on ASCII. And you'll see that if I list that file again, this time around, it's only RW nothing, right? I'm no longer able to execute this file. So if I do something like trying to run this program again, it says permission denied. Right? I'm not allowed to run this program. So this is all very good. Is there a shorthand for this? Right? There's a shorthand for this. I'll show you. If I say chmod 750 ASCII, this will restore the original rights that I had. Right? What's the magic trick I just did? I said chmod 750 upon ASCII, and this made this RWX R nothing X, nothing, nothing, nothing. Right, the trick here is this is just kind of a neat little shorthand that says I want a chmod for the 3 categories of users, you the user, your group, and everyone else, each represented as a separate digit. And for each digit, it's treating it as a 3-bit number. Right? A 3-bit number, 111, means read enable, write enable, execute enable. And a 3 binary digit, 3-bit number, 111 is 4 plus 2 plus 1, that's 7. So 750 means all access is enabled for the user. 5 is 4 plus 1. So 4 plus 1 means read enable for my group, execute enable for my group, and disabled write for everybody else. And then finally, the last digit is 0, indicating no permissions for everybody else. Right? So what if somebody in class tells you, hey, let me show you a trick, right? You're trying to dupe me and say, I've got PA2, right, ls, PA2, answer, I've got the PA2 answer key here. And what if I did chmod 777 on this directory? What disastrous consequences would that have? Yeah, so Jedrick's got it. It would leak the answer key, right? It would mean 777 for everyone else is also 7. So everyone who has an iLab login address account will have read, write, and execute access to the PA2 answer key, right? So this is just kind of a shorthand for using the chmod command. All of this is just to motivate. Knowing bits and bytes shows up in a lot of places. Okay, so the next few slides are somewhat tedious. Okay, maybe I went through that too quick. We've got some questions on the chat asking, wait, what do you mean by 777? What does that do again? Let me just work through that, right? Because I think I kind of didn't explain that as clearly as I could. Right, so chmod. 750 mode on the program called ASCII. This is broken down into 3 different user groups. 750, so it means for the user, read, write, execute. 111 is 4 plus 2 plus 1 equals 7. So read enable, write enable, execute enable is 111. That adds up to 7. For the group access is going to be read, write, x, 101. So read enable, write disable, execute enable. This is going to be 4 plus 0 plus 1, that's 5. And then finally for everyone else, anybody who has an iLab access is going to be read, write, execute 0, 0, 0. So that's 0 plus 0 plus 0, that's 0. Right? So 750 means these access permissions there. Okay. So any questions before we head on to the next little component? All right, so the next few slides are all about operations. So in Java, we were always drilled to distinguish between a single ampersand and double ampersand. Anybody want to tell us what's the difference between these two operators?
And is like pointing, it shows that it's pointing to an address, and is a Boolean function, essentially.
Good guess. So single ampersand could in C, yeah, ampersand does have something to do with pointers. It's the get the address of operator, but it also means bitwise and. Versus 2 ampersands, this is logical and. Right, so what we'll do now is we'll study very quickly what are these bitwise operator. Some of it will be new, some of it will be review of what the bitwise operators are. So if you have a bitwise operator of a single tilde, this is the bitwise not. And so we can study this now, right? So we can say if A is 0B1000000, what is this number? $128? How do we figure 128? We've got the 1's digits, the 2's digits, the 4's digits, the 8's digits, 16's digit, 32 digit, 64 digit, 128 digit, right? And there's a single 1 in the 128 digit. So this is the number 128. So I can write code now, right? I can say if I have int a equals 128, printf %d, new line, the number tilde a. What's this going to do? Right, so it requires to figure out what is tilde a given that. And what tilde a is just takes all the bits and bitwise flips them, right? So tilde a is tilde applied to a represented as a binary number, 1000, 0000, and it flips all the bits, right? And so it becomes 1 in the 1's digit, 1 in the 2's digits, 1 in the 4's digits, 1 in the 8th digit, 1 in the 16th digit, 1 in the 32 digit, 1 in the 64 digit. You add that all up, and it will give you 127, right? So printf tilde a is going to give you 127. And this is how to interpret why that's so. We can keep going. So we can even do things like please printf as a number /n 3 ampersand 1. What's this going to print out? Same approach, right? It's going to take 3, write that down as a binary number. It's going to write down 1 as a binary number. And it's going to apply bitwise AND, right? So bitwise AND, what it will do, it will look at each bit at a time and perform bitwise AND on it, right? So 1 bitwise AND 1 is going to be that row there. So that's a 1. 1 bitwise AND 0 is going to be 0, according to this row here. 0, 0, 0, 0, 0, 0, all of those are going to bitwise AND to become just plain old 0. So we got this number here, right? So it will print out what the value of 0b 0, 0, 0, 0, 1. And what's that? That's the number 1. Right, so this leads to some kind of very unintuitive but completely well-defined results, right? 3 bitwise AND 1, that's 1. We can do some other exercises too. So the single type, single bar, this is bitwise OR as opposed to double bar, right? Again, this is bitwise OR. Double bar is logical OR. And we can do perfectly well-defined results here too. We can say printf as a number, the number 3 bitwise OR 1. And what's that value going to be? Well, we can do the same thing, right? This will print out 3 and 1 as binary numbers. I'm going to perform bitwise OR on these numbers, and that's just going to work through it bit by bit. Look at every single bit. So 1 and 1 OR together is going to be 1. 1 and 0 OR together is still 1. So it'll print out the number 0011, and that is 3. Right? So you can see how this works for something like 2 and 1. Just the final example here. 2 as a binary number is going to be 0b 0010. 1 as a binary number is going to be 0b001. Bitwise OR those together. It will look at it bit by bit. And we've got 0, 1, that gets 1. 1, 0, that gets 1. 0, 0, 0b 0011. Right? So that also equals 3. Right? Just a simple set of rules to define how all of this works. You can work this through for even something like bitwise XOR. So just to work through this, so what's the difference between OR and XOR? Difference between OR and XOR? Yeah, right. The key thing about XOR is it's exclusive, right? The fun thing about XOR is with A and B XOR together, both are 1, that gives you 0, right? That's the only difference between this truth table versus the bitwise OR's truth table is this last row here. And we can work through this in detail, same thing. A valid thing to ask is printf, ooh, that's not the one I want. Printf as a number, the value of 3*1. Tricky thing. This is not power, right? Just remember that. Another rookie mistake. 2 rookie mistakes we want to avoid today. Padding with 0 gets you octal. That will get everybody at some point in your life. And the other thing is in C and Java, this is not 3 to the power 1, right? Just don't make that mistake. In some languages it might be, but not in Java, and not in C. We can work through what this represents. So 3 XOR 1 is 3 and 1 as binary 0B0011. 1 is 0B0001. And bitwise and them together. We work through them bit by bit. And the key difference here is 1 XOR 1, that is 0, right? According to this last row here. 1 XOR 0 is 1, the rest are zeros, so it will print out 0B0010, and that gets you 2, no problem. Okay. We've got 8 minutes. So in 8 minutes, let's work through this, right? So in 8 minutes, we're going to go to the laptop. And we'll work through a fun little program. Which logically, don't be scared, right? Logically, I put this in the PA3 folder now, right? Even though we're still working on PA2, it's in PA3 because this is about bits and bytes, right? I've got an example program called in-place swap. And what in-place swap does is a swap program again. But this time around, we're performing swap in a very strange way. So it is claimed that this program will successfully swap these 2 numbers. So we can show its printout, right? So before calling in-place swap, A and B are 2022 and 211 respectively. Right, I should update this, it's now 2024. And after in-place swap, the 2 values get swapped, right? A becomes 211 and B becomes 2022 or 2024. But if you look inside the in-place swap code, it does something very strange, right? It is performing all of this using just the bitwise XOR operator. And isn't that kind of peculiar? How does it manage to swap this way? Right, indeed, swapping takes place. So let's go back to the slides and work through a quick explanation of how swapping is taking place. All right. The code that performs swapping is it's got y equals x XOR y. Then it does x equals x XOR y. And then it's got y equals x XOR y. And we can plug each line by line, right? So we've got y equals x XOR y. So after executing this next line, x equals x XOR y, well, what's y at this point? It's been written to x XOR y, right? So what this is going to be is x XOR x XOR y. And what's the rule here? XOR is associative, so we can re-parenthesize this. This is just going to be x XOR x XOR y. And what's x XOR y? X XOR x always going to be?
It's going to be 0.
Yeah, so it's always going to be 0, right? You can look at this by seeing that if you do something like x XOR x, it's like saying a XOR a, right? No matter if a is 0, a XOR a is going to be 0. If a is 1, a XOR a is also 0. So you're always only going to look at these rows where a XOR a is 0. So same logic applies here. X XOR x, that's just 0 XOR y. And what's 0 XOR y always going to be? So we can scroll up, right? So suppose that we have one side is now 0. Well, no matter what b is or what y is, the output is the same, right? So anything XOR 0 is just itself. So now that becomes y. So at this point, the register or the variable x is storing y. Cool, right? And now how do we get x into y? So we could do the same. So at this point in the code, y equals x XOR y. Well, what's x at this point? We've claimed that y is now, we've claimed that x is now y. And what's y? Well, y is still this value here, so it's going to be that. The XOR operator is commutative, so we can swap the positions of y and x there. It's also associative, so we can re-parenthesize like that. Anything XOR itself is again 0, remaining x. So anything XOR with x is just x. So at the end of that, y will get x. Right? So successfully, what this completes is x at the end is going to have the original value of y, and y is going to have the original value of x. And that's a tricky, kind of cute little way of implementing swap using the XOR operator. Okay, we'll probably have to revisit this just a little bit on Thursday's class. The final takeaway is, again, don't confuse these things. Bitwise has a very special meaning. It goes through the data bit by bit and performs each of these operations on them. while the logical operators, the logical not, the logical and, the logical or, the logical not equals, all of these are what we're more familiar from the programming that we've done so far. Okay, so that's good. It's a good place for us to pause. So we've gotten up to today through working with bits and bytes, right? And then so on Thursday, we'll come back, review a little bit, and then we'll launch into how to represent negative numbers. All right, so with that, we'll end here for today and see you all on Thursday.
Have a good day, Professor.
Yeah, take care.